So today we're talking about generalized linear mixed effects models. This is I think the planned schedule. We're starting a little bit late because I got here a little bit late, apologies. But we'll plan to take a break of about 10 minutes between 10:50 and 11, and then get back at 11. I don't think we'll actually go until 11:50. I think we'll probably end a little bit before that. But I can stick around and answer questions that people have. Okay, so today's talk is about generalized linear mixed effects models, but let's start by talking about linear mixed effects models. So right off the bat, I have a poll everywhere question for you. So just go activate it. Oops. Sorry, there's lots of windows blocking screen. So now if you go to polleverywhere.com, you should be able to see. I'm just going to change the way that I'm sharing my screen so that it will be easier to interact with Poll Everywhere. All right, so here we have the results coming in. What are the big ideas you remember from linear mixed effects models? It's like we can only see one response at a time on my screen, but feel free to upvote. See something that you also remember. Did not attend the last session. Fair, fair. All right, I'm going to start walking through these. So if you did not attend the last session, that's totally fine. Don't worry about it. Can account for hierarchical structure in data sets. Absolutely. So that is one of the primary purposes of linear mixed effects models, or just mixed effects models, is to account for this hierarchical structure. Classic example, in education, you have students which are nested within classrooms, which are nested within schools, which may be nested within districts. So you can also have hierarchical structure in the sense of you could have just multiple observations nested within a single individual, which would occur in a longitudinal setting. Or you could have multiple observations nested within a single sample, for example. So I think in the last training session, someone brought up the example of having a slide and taking multiple samples from that same slide. So in that example, the observations would be nested within the slide. So that's great. When to use random effect and how to interpret, great. So we're going to be talking a lot about interpretation today. We have fixed, random, and observable, unobservable elements. Great. So typically in like a linear, just straightforward multiple regression, we have fixed effects, which are fixed parameters. They're assumed to be unknown and they're constants. They're not random. With a mixed effects model, we add in these random effects. So these are parameters that we're assuming to be random. And I'll talk more about that in a second in more detail. You can't just use a linear regression when all the data points are not independent of each other. Great. Independence is a major assumption of linear regression, useful for modeling cluster data. Not much. Okay. Well, hopefully we will jog your memory. Okay. So getting back to this. Okay. So linear mixed effects models. So with traditional linear regression, we have some outcome, which is a linear function of our covariate or explanatory variable plus some random error. The problem, as we've already talked about with that poll everywhere question, is that we assume that the observations are independent. More specifically, we might say that we assume that the errors are independent of each other, conditional on the explanatory variable. Whichever way you say it, independence is a fundamental assumption of standard regression. In contrast, cluster data are correlated. So there's a mismatch between the data and the standard traditional linear regression. So if we try and proceed with traditional linear regression, we're going to get incorrect standard errors, incorrect confidence intervals, incorrect p-values, all that. So our solution, which we talked about last time, was to add a random intercept. So I put it in blue here. So we're assuming that this beta naught I is specific to the ith cluster and is random. Typically, we assume that it's normal with mean zero and some variance. And this will induce correlation between our observations. We can also add a random slope or other random coefficients. But the key idea is that we are introducing these random beta parameters. Okay, so just as a reminder, here's a visual representation of the idea of these random parameters. So in the upper left-hand corner, we have simple linear regression with only fixed effects. You can see that we've drawn one single line through our cloud of points. In the upper right-hand corner, we have a random intercept and a fixed slope. So the different colors correspond to different clusters. Each cluster has its own intercept, alpha 1, alpha 2, alpha 3, but the slope is the same for each. So that's why those lines are parallel. Lower left-hand corner, fixed intercept, random slope. So you can see that there's one alpha for each of those clusters, but then there are different slopes for each cluster. So there are no longer parallel lines, although they all have the same origin. And then finally, in the lower right-hand corner, we have random intercept and random slope. So each cluster gets its own line, including its own intercept and its own slope. So hopefully this drives home the point of the linear mixed effects models. All right. So other things to note, conditional on the x, the y is assumed to be normal. So the error is assumed to be normal. Our random intercept in this example is assumed to be normal, which means that our outcome is assumed to be normal. That is a pretty big assumption that defines some data, but definitely not all data that we might observe in our work. So we have a new problem, which is what if your data are not normally distributed, conditional on the covariates? How do we address that? Well, we're going to use generalized linear models. Before we talk about generalized linear mixed effects models, let's return to just straightforward traditional generalized linear models. So if we go back to poll everywhere, move on to the next question. Very similar. What are the big ideas you remember from generalized linear models before we consider any random effects? Great, 3 responses. Okay, we can proceed. So it can be used, oh, here we go. Response can be any exponential family distribution, not just normal. Great. Exponential dispersions family specifically. But yes, not just normal. We don't need our outcome to just be normal. Can be used for non-normal response variables. Great. There is a link function relating the covariates to the outcome. Exactly. So we have to select a link function that's going to connect the expected value of the outcome to the covariates specifically, and covariant structures. So covariant structures, those are going to come up more so in generalized least squares. So generalized least squares is when we have some arbitrary covariance matrix sigma. This general covariance structures are also going to come up in generalized estimating equations, and they are induced by random effects that we introduce to the model. So those are going to be more so when we're talking about non-independent data. Okay, great. So I'm glad that we got to jog your memory a little. So again, traditional linear regression is that the problem is that the observations, specifically the outcome, are assumed to be normally distributed. The error conditional on the covariates is assumed to be normally distributed, and lots of data are just not normally distributed. So the problems that can arise are impossible fitted values, incorrect standard errors, and some other issues as well. So how do we address this? Usually we use the generalized linear model, or GLM. So what do I mean by that? So with the GLM, we assume the data follows some distribution belonging to a broader family of distributions than just the normal. This is the exponential dispersion family. I'm not going to define this now, but I can talk about it more outside of training. But suffice it to say, I can give you some examples. So examples of distributions in this family: normal. So standard traditional linear regression does fall into this broader class of models. Also a Bernoulli outcome, so 0 or 1, Poisson, count outcome, gamma distribution, so positive values that are skewed, inverse Gaussian, and then a negative binomial. So these are just some examples of distributions that are in this family. And you may have used these in your work. All right, so in addition to assuming a specific distribution of the outcome, we also assume a specific functional relationship between the covariates and the mean of the outcome. So this was brought up in the poll everywhere question. So for comparison purposes, let's just look back at traditional linear regression. We're connecting our expected value of the outcome, conditional on the covariate, to the covariate through just this linear function, traditionally. With linear regression, the mean of the outcome is a linear combination of the covariates. With GLMs, some function of the mean of the outcome is a linear combination of the covariates. So I've added this G function, which is very general as of right now. So what we're saying is G of the expected value is equal to, in this case, with simple linear regression, beta naught plus beta 1x. Or in more complex cases with multiple linear regression, just some linear combination of our covariates and an intercept. So this raises the question of how do we choose G? I'm sure you do this in your work already. We want something that's going to respect the possible values of the expected value of y, conditional on x. And you want something that's going to ascribe meaningful interpretations to our coefficients that we're estimating. So what do I mean by that? Well, let's consider an example. So suppose that our outcome is just binary. So we'll say y equals 1 if the patient is cured, y equals 0 if the participant still has some disease. We're also going to, just for simplicity, consider this binary covariate or explanatory variable. X equals 1 if the patient received the drug, and 0 if they got the placebo. So clearly the outcome is Bernoulli, so that's the distribution we're going to work with for our outcome. The canonical link function for this distribution is the logit, or the log odds. So we're saying that the log of the ratio between the expected value of our outcome and 1 minus the expected value of the outcome is equal to this linear combination of our covariates. So this is going to respect the values of the expected value of y, because for this example, expected value of y has to be between 0 and 1. So if we plug some number between 0 and 1 into this function for this expected value, everything's going to work out just great. Also, if we get estimates of beta naught and beta 1 and are trying to get a fitted value for our outcome, we can plug our covariate value and our estimates into the right-hand side of that equation. And then once we transform it, we'll get something that makes sense. So I guess what I'm trying to say is the inverse function of this g function is going to give us values that are between 0 and 1, which is what we want. Oh, I have another polar variable question for you. All right, how do you interpret e to beta 1 in real world terms for this example? So just as a reminder, I'm going to put back up the slide so everyone can see it. But the question is, how would we interpret either beta naught or e to beta naught for this particular example? I'm going to switch back quickly to polar just to see. Okay, no one's responded. Keep thinking. Take your time. Okay. We have some responses, so maybe we can talk through these. Odds ratio. Odds of being cured if you are in the drug group as compared to the placebo. The odds ratio of those who receive the drug versus those who receive placebo. Change in odds in the treated population compared to placebo. Great. Okay. So yeah, this is an odds ratio. Once we exponentiate this beta 1 coefficient, we'll get an odds ratio. The odds of being cured if you are in the drug group as compared to so this is very close. It's the ratio of these two odds. So it's the ratio of the odds of being cured if you're in the drug group to the odds of being cured if you're in the placebo group. So yeah, these are great. Yeah, fantastic. So that should have just been a bit of a review of interpreting coefficients in generalized linear models. Oh, and here's just working through how we arrive at that, if you're curious. I think I have just a reiteration in English language. So e to beta 1 is the ratio between the odds of cure if the participant takes the drug to the odds of cure if the participant takes the placebo. All right, I have a second example for you. That was a binary outcome. Let's talk about a count outcome. So we'll say that y sub I is the number of new tumors in 1 year. X sub I is 1 if the participant takes the drug, 0 if they take placebo. We might assume that the outcome is Poisson. We don't have to make that assumption, but that's typical. And the canonical length function for this distribution is the log. So we're taking the log of the expected outcome and setting that equal to our linear model. All right, so as you might have guessed, I'm going to have you answer another question. So same question, but now for the second example with a count outcome. Do we have responses yet? Let's actually, so keep submitting to poll everywhere. Just for those of you who are in the room, let's take advantage of the fact that we're in the room together. So maybe just turn to someone nearby and discuss your thoughts about what you think the answer to this question is. Go ahead. This is not a ratio. It's just the cap.
I wish I could. It's exponentially.
It's just the original.
Oh, right.
It's the cap.
So it's just the average number. Expected tumors in 1 year.
Yes.
Because drug burns. Okay.
This.
It's gonna last long.
All right, it's sensible. So let's look at the responses. Change in average counts in treated population compared to control, the risk ratio. Oh, we got 2 responses. Okay. So I want to address the second one first. So risk ratio, risk we generally think of as probability of observing some outcome. So this would generally, if we're talking about a risk, it would generally be with a binary outcome. This does end up being a ratio. We might think of it as a rate ratio if we had an offset in the model. So the way that I posed this was that y was the number of new tumors in 1 year. So I specifically said we're only working with time periods of 1 year. If we were following people for different time periods, we could incorporate the length of, or the duration of the time period of observation into the model as an offset. And then what we'd be working with is rates as opposed to counts. So just wanted to address that finer point of Poisson regression. And then I think I'm going to skip to this next page just so we can see a bit of the math. So e to beta 1 is going to be a ratio of 2 expected outcomes. So it ends up being the ratio between the expected number of new tumors in 1 year if the participant takes the drug to the expected number of new tumors in 1 year if the participant takes the placebo. So it is a ratio. This time it's a ratio between expected counts. Relative risk? Maybe. I mean,
relative to the ones who get a placebo, then the average number of tumors for those.
yeah, absolutely. That sounds great. Any other questions or comments over here? Cool. So that was supposed to be a bit of a refresher of generalized linear models traditionally. This last bullet point is just about that offset I was talking about. Okay, so now that we've reviewed linear mixed effects models and generalized linear models, we're going to combine them. So generalized linear mixed effects models, we're combining these 2 categories of analyses. So from linear mixed effects models, we're going to take random effects that we assume are normally distributed. From generalized linear models, we're going to take that we have an assumed distribution of our outcome, which is usually not normal, and a link function between the mean and our linear predictor. So our linear combination of our covariates. So for example, on this top row, I'm using the canonical link function for a binary outcome, and I've just added in a random intercept. And then for the second line, canonical link function for a count outcome, and added both a random intercept and a random slope. So now I'm going to talk about implementation. So I'm going to talk about implementation in the context of this particular study. So this is a skin cancer prevention study, which is a randomized, double-blind, placebo-controlled clinical trial of beta-carotene to prevent non-melanoma skin cancer in high-risk subjects. This is a pretty old trial, but that's why we have all the data for it. We have over 1,800 participants. who were examined once every year for 5 years. There's no baseline measurement in the data set, so we have a maximum of 5 observations per participant. The outcome is the number of new skin cancers in 1 year. Just in case you were curious, I did check. No participant missed a visit between 2 other visits. So we can rest assured that these new skin cancers were observed in 1 year periods. And I don't think anyone missed baseline. So everyone is being observed for the same duration of time. Here are our variables. We have an ID, which clinical center the participant was recruited at. There were 4 different clinical centers. Age and years at randomization. Skin is this variable that's binary. So people were categorized based on their likelihood of burning if they spent time in the sun. Gender, we just have male or female. Exposure means the number of previous skin cancers. And like I said previously, these people were all high risk. So some people had lots of previous skin cancer. Y is our outcome, number of new skin cancers in 1 year. Treatment, beta carotene versus placebo. And then year is the study visit, so 1 through 5. All right, so I have another question for you. What would you do for exploratory data analysis? So I'll give you a second to think about that. Here again are the variables in the data set. And if you're in the room, some of you are already doing this, but feel free to talk to each other. You can discuss your thoughts. What would you do? Check. Okay, we have some suggestions. Prepare baseline characteristics. Oops, lost it. First, look at the data, descriptive stats. Wilcox ranks them between the independent variables and Y. Univariate linear regression, multiple regression. Great. These are all great suggestions. Check pattern of missing mix. That is a great idea. I can say that for this data set, we'll get to this. We'll get to this. Because I did some exploratory data analysis. Table the demographics, ensure there's balance in age. Great. Skin type, gender, and exposure between treatment groups. Treatment versus new cancer to visualize. Look at distribution of variables, great ideas. These are all fantastic ideas. I will keep these and I will add them to my arsenal for exploratory statistics. Okay, so I did some exploratory data analysis. So I can just show you what we did or what I did. So first off, here's a plot of the number of participants per year. So going back to what someone said about missing data patterns, you can tell that we have dropout, especially at that last time point. By the time we get there, we've lost a lot of participants. And this is color-coded by center as well. This is also telling us that center, what color is that? 4, I guess, has the most participants in it. Okay. Here, what do I have? I have the relative frequency of people for each value of number of new cancers per year, and also split out by the 2 treatment groups, or treatment and placebo. So this might give us maybe an idea of if the treatment is effective. If we see that, like in beta carotene group, we're seeing more people with zeros than in the placebo group. It's not super obvious at first glance. Here I broke up the relative frequency of number of new cancers by male or female, it does appear that we are seeing that among men, it's more common to have more than 0 cancers than among women. Here we're splitting based on tends to burn versus does not tend to burn. If you tend to burn, it does seem that we're getting more non-zeros. Well, hard to tell. All right, here we have a continuous variable age at randomization. And I'm looking at cancers per visit. So the average of for each participant. So each dot here is an average for a given participant, the number of cancers per visit. Maybe there's a slight relationship. That blue line is just a simple linear regression. Here I've logged the outcome. So log of cancers per visit plus 1. And we're looking at the relationship between that and the age at randomization. It does seem that the older you are, you have more cancers per visit. Number of previous, I spelled previous wrong. Number of previous cancers. So this is that exposure, exposure explanatory variable versus cancers per visit. This does not seem to be super linear, at least once we get to more than maybe 12 previous cancers. And then here's the same thing, but with a logged outcome. Just anticipating that we're going to use the log length function. Okay. So I did want to point out, we do have these two, you can see in the upper right-hand corner, there's 2 values that have lots of new cancers per visit on average. So I wanted to address those. So these are those 2 observations. You can see that we have here. They're both at the same center. One's in their 50s. Oh, they're both men. Both in their, so one's in his 50s, one's in his 60s. So they each had 21 previous cancers. One is in the placebo group, one is in the treatment group. Total cancers. Yeah. Yeah, this is a lot. So each year we're seeing about 10 new cancers for each of the participants. 9.8 cancers per visit is over twice as much as the next highest participant. So that's a lot. I will say that 21 previous cancers is not as unusual. So there were other participants with that many previous cancers. So it's more the outcome that is unusual. I think I just left these participants in, but you might make a different decision. For you, maybe try it both ways, leave them in, take them out, and see if that has a huge effect on the results. All right, anyway, we have several decisions we have to make. What distribution we're going to use for our outcome, what length function we're going to use, and which fixed effects we should include and which random effects we should include. So I'm making some executive decisions just for the purposes of maybe I could allow you some input. What is my next question for you? Okay. I am curious what distribution you think we should use for this. Feel free to. Again. Seems like we have consensus. All 3 of these people have suggested Poisson. I agree. This is a reasonable first approach. So we often go through this 2-step process with count data. I'm not saying you do this every time. I'm not trying to say this is universal, but it's relatively common to start with Poisson and maybe use quasi-Poisson if the data are over dispersed. So quasi-Poisson is not an option with GLMER, which is the package. No, this is the function we're going to be using today. The package is LME4. So quasi-Poisson is not going to be an option for this mixed effects models approach with a count outcome. Mixed effects models are fit with maximal likelihood, and quasi-Poisson regression uses a quasi-likelihood, not a real likelihood. If you're super wedded to using a quasi-Poisson regression and you have correlated data, my recommendation is that you use generalized estimating equations, or GEE. Both of these methods fit into an unbiased estimating equations framework. So unbiased estimating equations, that's a very general theoretical approach. And both quasi-Poisson and GE fit into that approach. So if you really like quasi-Poisson, I recommend that you go with GEE. If you have over-dispersed count data and are using mixed effects models, my recommendation is that you try out a negative binomial distribution, because it will allow you to use a true likelihood. I will say, if you search online, there are definitely methods to use quasi-Poisson and a mixed effects model. There are other packages, other functions you can use. I mean, like do whatever floats your boat, I guess. My recommendation, based on this theoretical backing, is to use quasi-Poisson with GEE and negative binomial with mixed effects models. All right. So I think so when I was doing the data analysis, and in the R file that I will post to the like shared Google Drive afterwards, I tried out all three of these different distributions. For Bernoulli, I just dichotomized the outcome to 0 or more than 0. What link function should we use? For each of those distributions, I use the canonical link function. For fixed effects, I use age, whether or not the person tends to burn, their gender, number of previous cancers, and an interaction between treatment and year. And then for random effects, I use the random intercept for each participant. You might make different decisions. That's totally reasonable. This is just for the purposes of this training session. All right, so now I'm going to talk about how to present this and how to do this in R. So like I said, we're going to use the package LME4, and the function of interest is GLMER, which is like a combination of GLM and LMER. Hopefully that's intuitive. So I fit this model. So with the random effects and the fixed effects that I had identified earlier, you can see that we're still using the same syntax from linear mixed effects models of the parentheses to indicate what effects are random. And then I'm just adding this additional argument, family equals plus on, because we have a count outcome. I did get this error, model fails to converge. Also, model is nearly unidentifiable, very large eigenvalue. And it's actually recommending that I try rescaling my variables. So I actually did that. I rescaled the age. So I subtracted off 30. So now age scaled of 0 is going to indicate that the person is 30 years old. And then I also divided by 10 so that now the unit is 10-year increments as opposed to single-year increments. So fit the same model, but with scaled age. It still failed to converge. So we got rid of one error, but I still have a convergence issue. What did I try next? Yeah, so I changed the control option to get, I think just to get it to do more iterations. Still had a convergence issue. I changed the optimizer and this one works all the time?
Yeah, that kind of works. I never understood why, but that kind of the solution for every type of error that comes out of that.
Yeah. So yeah, you might have to troubleshoot. Sounds like this one is maybe you should try this one first if you get similar errors. Yeah, good question. So because we're fitting these models with maximum likelihood, we need to maximize the likelihood. And so it's optimizing by finding that maximum.
What's the default if you don't say? Or it's just the mechanism?
Yeah, I forget what the default is. I can actually just do a quick Google search of BOP YQA. This is an acronym, but I forget what it stands for. Bound optimization for quadratic approximation. So these are just using different numerical methods. Yeah. And I'm not sure what the default is.
That make us like worry about the model we're fitting if we're getting those optimization errors, or is that just like a technical thing?
Yeah, that's a good question. I think you should ask yourself, is there an issue with the model that you're fitting? So actually first, when it gave us this original error of like model is nearly unidentifiable, that definitely made me question whether there's something wrong with the model. It turned out not to be an issue with the model, but yeah, so I think it should make you question if there's something wrong with the model. There are further diagnostics that we can do to check further about that, which we'll go through. Other questions or comments? Okay. Here's the output. I think I even cut off some of the output. So this is just most of the output. I think I'm going to highlight some of the pieces of this. So note that it's fit by maximum likelihood. So when we did the linear mixed effects models, we were talking about REML versus just ML. REML is not an option for these generalized linear mixed effects models. And just to say why, with REML, if you remember, we were working with a linear transformation of our outcome. That doesn't make sense for this outcome now, which is a count outcome. We don't want to be doing linear transformations of our non-normal outcome. So we're not going to be using REML. It's just always going to be fit with maximum likelihood. You may have also noticed that the output said Laplace approximation. So in order to compute the likelihood, you have to do a very difficult integral. And so this integral is approximated. You can change the method of approximation with a parameter in the function, NAGQ. I'm not actually sure what that stands for. The default is Laplace approximation. And the way you change that parameter is you give it different numbers. So the default is that it's set to 1, which corresponds to a Laplace approximation. If you increase the number, then it's going to get a more accurate approximation, but it may take more time. And also for certain complex models, it's actually not going to even do it. I don't know if it will give you an error or what, but for certain complex models, you just have to use the default Laplace approximation. And what does this mean? What is this Laplace approximation? We can talk about that outside of this training. It gets complicated. All right. Also, in the output, you may have noticed groups. So the groups are identified by ID because ID indicates a participant and the groups are the participants. And it's telling us that there are 1,683 groups. I had originally said that there were 1,805 participants. I don't know what happened to the other participants, those 122. R didn't remove them. They're just not in the data set. So I can post the original paper that corresponds to this study. I don't think it addresses who those 122 people are, but they're missing. And then finally, we can see in the output that the p-value is labeled with probability that we're greater than some z-value. So GLM-ER does give p-values. You may remember that when we were working with LMER, there were no p-values. GLM-ER does give p-values. They're based on the standard normal distribution, not the t-distribution. So we're not even going to bother with Satterthwaite approximation or whatever. We're just using the normal distribution. All right. So that's just highlighting some aspects of the output. I do have a polar everywhere question, and I also can see that it's 10:49, and I promised a break. So what I'm going to do is I'm going to activate the next poll everywhere question. Feel free to respond. This one is multiple choice. So feel free to respond to that. Because it's 10:49, I do want to take our break. So I'll leave this question up. We'll take a 10-minute break. We'll return at 10:59 and address this question. So I'll see you in 10 minutes. Welcome back, everyone. Okay, so we were discussing this question. The standard deviation of the random intercept is 1.5. 141. What are the units? New cancers, log new cancers, log new cancers squared. Wow. Okay, 100% of the people said log new cancers. Is that correct? Yes, good work. All right, good to know everyone got that right. Okay, returning to our analysis, how do we interpret the results? I'm not going to ask you to do that yet because it would be a trap. Interpreting coefficients in generalized linear mixed models is tricky. So I think we should consider a much simpler model while we're talking about interpretation. So let's just think again, y, still number of new cancers. Well, y sub ij, number of new cancers for the ith participant, the jth time point. Let's just say we're going to focus strictly on group membership. So xi equals 1 if the ith participant was in the treatment group, xi equals 0 if they were in placebo group. So our mean model is this. So I'm using, because we're talking about the Poisson distribution, I'm using the canonical length function, which is the log. You can see that I have our straightforward beta naught intercept, beta naught I, which is the random intercept, and then a fixed slope. So if we interpreted e to beta naught, it would be the expected value of our outcome when xi is equal to 0 and beta naught I is equal to 0. So what does that mean? I'll just activate this. How would you interpret e to beta naught in real world terms? I'll put this up again so you can see it. Okay. We have one suggestion. I'll wait a little bit longer, see if we get more. But for those of you in the room, turn to a partner and discuss your thoughts about the answer to this question. Some kind of bridge. Is the average is about 1?
This is the fixed.
Of the fixed.
Right.
Yeah.
The average response for control patients.
See.
What exactly that's the problem. Those
Like this problem.
Yeah.
They're in
Average patients may mean a lot of things. So, yeah, it's something.
All right,
Maybe
let's
not.
see. What do we have? For an average subject, the expected number of new cancers in the placebo. Interesting. Mean number of new cancers for members of the placebo group. Okay. These are great suggestions. I'm gonna have to think through this. I always have to see it in front of me or to fully get it. So e to beta naught is the expected number of new cancers for someone in the placebo group with a random intercept of 0. And since the random intercept is normally distributed, the probability that the random intercept is 0 is 0. So there's a 0% chance that someone has this random intercept. So arguably, it's not super useful. Yeah, why? So someone had said for an average subject. So it is true that 0 is the expected value of the random intercepts. But we're not necessarily averaging across all the participants. So this is tricky. We're going to talk about it in more detail. Oh, this is, I guess, the next question. So is this the same? So conditioning on the random intercept being 0, is it the same as averaging across all the random intercepts? So I've done it out. I mean, you don't need to, you can look at this to your heart's content. But the end result is that if we average across the random intercepts, what we get is something that is strictly greater than e to beta naught. So unfortunately, the interpretation of e to beta naught is not the same as like our expected outcome in the placebo group for an average participant. It's for a specific participant. And this is why interpretation is so tricky. And if we look at this, it's really because of this non-linearity that's going on, because we're using this non-linear link function that is causing issues. So what we've identified here is the difference between a conditional parameter and a marginal parameter. So e to beta naught is a conditional parameter. We're conditioning on a specific value of the random intercept. And since these random intercepts are continuous random variables, the probability that they're the same is just 0. So conditioning on a specific value of the random intercept is the same as conditioning on a specific individual, because no other individual is going to have the same random intercept as them. In contrast, the thing that I found on the previous slide, expected value of y given x equals 0, so just averaging across all participants in the placebo group, that's a marginal parameter. We're averaging across individuals. We're going to keep talking about this, but are there questions right now?
You
Yeah.
have more time why the first one is equivalent to conditioning on a specific individual.
Yeah. So, yeah, absolutely. I think, yeah, so beta naught sub I equals 0. That doesn't really correspond to any identifiable person. Like,
Right.
yeah. So that parameter e to beta naught corresponds to someone theoretically, but not someone in our study. Yeah, so that's why it's not useful. Other questions?
The expectation is still over the, like, I over the patients, or in both cases?
Only in the second case. Only in the second case are we averaging across patients and averaging across different, yeah, eyes, different indices. We're going to keep talking about this. So definitely pause, raise your hand, put a question in the chat if something comes up. But we'll keep addressing this. Okay, so just returning to this simplified version of the study that we're talking about, where we're only considering one covariate, specifically group membership. Now talking about beta 1. So e to beta 1 is equal to this ratio. So knowing that, how do we interpret it? We'll activate this. and return to the slide so you can see what we're doing.
Yes, but there's still the conditional element of that. Because it would be like, this would be like average.
If you haven't already and you're in the room, maybe turn to someone next to you and discuss.
So. It's the change.
That's for sure, but it's.
The ratio. Average. Since everything's between trend.
Yeah.
If it's to be worse.
That's not. But I guess for conditioning.
For each, the.
Response on that patient.
Zero I for
Yeah.
confusing me, yeah. I think I just answered that, just conditional on this.
Still.
I guess if you expand out each of those expectations, this. Beta doesn't cancel.
All right, let's see if people have, ooh, okay. Ratio of number of expected new cancers for a participant in the beta carotene group versus a participant in the placebo group. Okay. Risk ratio between treatment group and placebo group averaging across all subjects. Ratio of the average number of new cancers in the beta. Per year. Okay, we have a variety of responses. Let's walk through it. All right, so we have a ratio. It's between the expected number of new cancers in the beta carotene group to the expected number of new cancers in the placebo group, conditional on the random intercept typo, 2 does. So what does that mean? We are conditioning on this random intercept. Like I was saying earlier, because the random intercepts are continuous random variables, the probability that we get 2 of exactly the same value is 0. So no 2 people have the same random intercept. So this thing is the ratio between the expected number of new cancers if the ith participant took beta carotene to the expected number of new cancers if the ith participant took placebo. In both the numerator and the denominator, we have the same random intercept, beta not I, whatever it might be. So we are making this comparison within a single individual. Yeah, Morgan, you're frowning. Tell me more.
We talked about this in the last section, but one of those is a counterfactual, right? Because you each only get one treatment.
Exactly. Yeah. Great point. We only observe each participant getting one treatment of placebo. So, yeah, this is an individual treatment effect, even though we don't have something to keep in mind. This does raise a question. So this is a conditional interpretation. What do we have next? Yeah, this is a conditional parameter. Is it the same as the marginal parameter? So if we average across all of our random intercepts, do we get the same thing? It actually turns out that you do. The math works out.
I wasn't expecting that.
Yeah.
Because random, just like other variance.
So this is one of the things that makes interpretation so tricky with these generalized linear mixed effects models. In this case, the conditional parameter and the marginal parameter are the same numerical value. So this E to the beta 1, it's the ratio between the expected number of new cancers across patients in the beta carotene group and the expected number of new cancers across patients in the placebo group. It works out. Sometimes the conditional parameter is the same as the marginal parameter, and sometimes it's not. Sometimes the conditional parameter is meaningful, and sometimes it's not. So I have this table, and actually I have to give credit to Sebastian Anuz in the biostat department at Harvard because I stole this from him. But in this table, we have for a specific link function and for a specific coefficient that we're trying to interpret. Do we get a marginal or a conditional interpretation? Where marginal is indicated by an M and conditional is indicated by a C. And it's going to depend on whether we are fitting random intercepts or whether we are fitting random intercepts and slopes. So in the example that I just gave, we are working with a log link. We tried to interpret both the intercept and the slope. In our fitted model, we only had a random intercept. So the intercept only ended up having a conditional interpretation. Whereas the slope, the value could be interpreted as a marginal or a conditional parameter. So hopefully this will be a useful reference for you moving forward. If you're analyzing data, you can return to this to help you figure out how to interpret these variables.
Regardless of the response distribution.
Yeah. Yeah, what matters is we are always assuming that the random coefficients are normally distributed. And so that's what we're averaging across. Other questions? It's tricky. So one final thing to say. The conditional parameter is often what a physician is interested in.
Sorry, John. So does this mean that when we interpret the random intercept, we should give both interpretations? The marginal and the conditional?
The random intercept?
Yeah.
Like if you get the empirical Bayes estimates or something?
Whatever, if I have to explain what does my result mean to a PI?
Yeah.
Because that's ultimately the hardest part. You may be convincing me with that integral, and I'm completely fine with that, but I cannot go to a physician showing in the integral. So I need to, if you have both interpretations, so probably the strategy would be just to lay out both interpretations, both the marginal and the condition. But
I think that's reasonable.
if they're different.
So you're only going to get one parameter value. And so I think if you're trying to communicate its meaning to a collaborator, if you can use both interpretations, I guess you could give them both. I think, yeah, you have to make a decision about what kind of information you're going to share to them.
Because one contains the variance, that tau square of 2, the other one doesn't. Am I right? Am I remembering correctly?
Well, so either way, you're going to get the same standard error for the parameter. But so if you're trying to convey the meaning of like, what is the meaning behind these random intercepts?
Yeah.
The way that I've done that in the past is by conveying that like each person has their own set point for a random intercept. So like I did an analysis like this in the context of use of force by police officers. Different police officers are more or less likely to use force. So I guess maybe in this example, each individual might have their set point of like how likely they are to get new cancers. But continuing with this theme of like how to convey this to a collaborator, my take, and you can correct me if I'm wrong, is that often a physician is going to be interested in this conditional interpretation. Like, what effect can I expect for my patient? And then maybe someone who works in population health might be more interested in the conditional, marginal, yeah. What effect can I expect for this population? You might disagree, I don't know. That's one takeaway that I've heard. All right, so we've talked about interpretation. Let's talk about actually checking if our model fits our data. All right, so recall that the random intercept is assumed normal with mean 0. As in linear mixed effects models, we can estimate the random effects rather with empirical Bayes estimation. And we can check if the distribution of our estimates actually looks normal. So here I have our empirical Bayes estimates and a histogram. So what do you think? Normal? Yeah, almost. Yeah, so let's address this. I do have a question for you. What do you think is going on? How would you check? So I can post the image again. All right, so maybe if you're in the room and you haven't already, turn to someone to discuss your thoughts on this question.
Right, this model was the one with only one covariate or all of them?
Good question. No, this includes all the covariates and just a single random intercept. So I will say that this is actually a very difficult question. It's not entirely fair. You don't have the data in front of you, so you can't actually do these checks yourself. But we can look at some ideas that people have suggested. Split up the histogram bars, coloring by different covariates. That's a reasonable suggestion. So we can definitely do that. I had the advantage of having these data in front of me and having time to try and figure out what was going on. So I do have a hypothesis about what is going on. So this is the same histogram. Instead of coloring bars by covariate values, I've colored them by the actual outcome. So the blue is for people who had at least one new cancer over the course of the study. The pink is for people who had no new cancers over the course of the study. So I think we have a mixture distribution. That's my hypothesis. I will say as well, I actually did not use blue and pink because I was concerned about red-green color blindness. And so I accounted for that in the PDF, but something about this display is making them sort of red and green. So I apologize if you are colorblind. Okay, so let's dig into this. So here I have another plot. On the horizontal axis, I have the fitted value. So this is the fitted value of the outcome when we have no random effects. On the vertical axis, I have the fitted value of the outcome with random effects. Each dot represents a participant. I think this is actually not just a participant. I think each dot is participant observation or participant time. There's also coloring. So the bluish greenish is people who had at least one new cancer. And the orangish is people who had no new cancers. And then the purple reference line is the line y equals x. So what we can see is the dots that are below the reference line have a higher fitted value without random effects in the model than their fitted value when you include random effects. So including random effects in the model is taking these people who had no new cancers at all and sort of smushing their fitted values down towards 0. So I think what we have is actually two underlying distributions. It's like a zero inflated model. Yeah. So you have some data generating process that is only producing zeros. And then some data generating process that is producing zeros and above. Without the random effects, you're not getting that. That's sort of getting lost. The random effects are accounting for maybe these two different data generating processes. I will say the distribution of the random intercept is the same when the negative binomial and binomial distributions are used instead of the Poisson. One argument might be that this is not the right analysis for these data. So which raises the question, why did I use them for this talk? They don't fit perfectly. So this is what happens with real data analysis. Then this might happen to you. You go into it with one plan, and then sometimes you have to adapt. So that's why I use these data. I will say, how do you proceed if it actually turns out to be the case that you have this mixture distribution or like zero inflated model? I don't have a good answer for you. You can probably find some way, you might be able to find some way of combining like zero inflation and this generalized linear mixed effects models. That's beyond the scope of today's talk. Besides random effects, what other diagnostics should we perform? It's actually difficult to find clear guidance on this. So here I've plotted the Pearson residuals as a function of the fitted values with a reference line just horizontal at 0. I don't know how informative this is. Maybe you disagree. We're seeing this banding pattern because the observed outcomes are counts. So there's that. I also have the deviance residuals plotted as a function of the fitted values. Again, I don't know how useful these are. Here's a histogram of the Pearson residuals, similar actually to the empirical phase estimates. And here's a histogram of the deviance residuals. Yeah. So I wish I had better advice for you when it comes to diagnostics. Definitely check out the empirical Bayes estimates. You might have to do I did do some research before this talk to see like, what can I tell you about diagnostics beyond just those empirical Bayes estimates? It's difficult to give you good advice. Is there anyone here who has better advice? What other diagnostic plots we should be making? Okay, TBD. We'll keep thinking. What about model selection? Since we're using maximum likelihood, we can use likelihood-based approaches for model selection. So AIC, BIC likelihood ratio test for nested models. So this is unlike with when we were using linear mixed effects models and we had to think about, are we using maximum likelihood or REML? This is just always going to be maximum likelihood. Again, be careful with the LRT. If the smaller model is the same as the larger model, but with a variance set to 0, you have to use a mixture of chi-square distributions to compute the p-value. So this is something we also talked about in the previous talk. I recommend consulting, I guess, the primary literature. I had given some references for the other talk that you can check out. So next steps, I just want to point out that these generalized linear mixed effects models make a lot of assumptions. We're assuming we know the likelihood in its entirety. aside from a couple parameters. They also estimate conditional parameters, which might not be what you're interested in. In contrast, GEEs make fewer assumptions and they estimate marginal parameters, which you might be interested in. And GEE is the next topic in this series. Like I said, I'm going to give a talk about GEE on October 15th. So if you're interested, definitely attend that talk. That's it for now. Here are some references. Also a request to fill out the evaluation once you receive it in your inbox. And now, any questions?
Yeah, you know what, probably after seeing that residual thing with the mixture. I don't know if I'm right, just. Probably. You could try and fit two models. Like take that variable out of the main model, like the how many cancers before, I know is that what was the subdivision, no cancers or
At least one cancer.
at least one.
Yeah.
And you fit two models to separate Poisson, GL, MNs. For those.
Yeah, so
And in
like,
that case, you should have normal residuals. I was.
yeah, so you're talking about sort of like starting with a logistic regression to see
Yeah,
predicting.
not necessarily, even this one, you see, oh, the residuals are so crappy, like
Yeah.
two hills, what went wrong? Okay, it's the just a position of two norms, right? So I can separate them out and fit two different models, same models to generalized effect, generalized linear mixed effect models, Poisson distribution on the outcome, but on the two subsets.
Sure. Yeah, you are creating those subsets based on the outcome that you observe.
Yeah,
But yeah, sure.
because if the residuals should be normal, clearly they're not.
Yeah, absolutely.
If I had to say what went wrong, probably it's not only one model. I don't know, maybe I'm completely wrong, but
No, I think that makes sense.
it would just be a try.
Yeah. Other questions or comments? Cool. Okay, we can stop there. Thanks everyone for coming. Definitely fill out the feedback form and we'll see you.
Thank you.
Good.